inverse limit. Okay.
Yeah.
Yeah, the inverse limit. Sorry. If you don't know this idea of an inverse limit, just think about it as taking union. Okay. So union of all the Galois groups where E ranges over all the finite Galois extension of that.
We can discuss these things after the discussion session.
Yeah. Okay. So G means the group with entries in F bar. So whenever we talk about some geometric properties, of GF, it actually means we actually mean the corresponding properties for the group over the algebraic closure. For example, the general linear group, special linear group, the special orthogonal group, and the symplectic groups. They are connected. And the orthogonal group is disconnected with two connected components. Okay. One of these is the special orthogonal group. The another one is the coset of this translated by a matrix with determinant -1. Okay. So you think about this, if F is a finite field, then these fixed point groups are always disconnected. Okay? So if I say the group is connected, we actually really means the corresponding properties for the group with entries in algebraic closure. So it's like the Lie groups that Tianfang Yang mentioned. Okay? So it's just the terminologies that are used by people who are studying linear algebraic groups. But we allow more general fields. Okay? Okay, any questions so far? Okay. Is that clear about the terminology here that I use?
What's the meaning of the GF closure?
Here. F bar variety.
The next line.
Here?
Yes.
Okay. So here, if I have, say, if it is a set that is acted on by a group G, then XG is the set of fixed points. So this is all the elements such that if you act by any element in G, then it is invariant under any action by the element in G.
Is here the F,
Sorry? F?
Or for any field, it is connected.
For any field, yes. For any field, yeah. Okay, so you may ask, if F is finite, then these are finite groups. So what's the meaning of the finite groups being connected? Okay, it really means the groups GL and C, for example. Okay.
Which topology? Which topology?
Which topology? Zariski topology. Zariski topology. So then I'll define some subgroups in a reductive group. So by the way, from now on, we always assume G is connected. Okay, so we are excluding this case. So there are a couple special types of subgroups in a reductive group. So the first one that I want to talk about is, all right? So it's the plural form of torus. So a torus T in G is a connected commutative algebraic group defined over F. Okay. And it is maximal if, in the usual sense, there is no other torus properly containing it. And it is split if it is if T is isomorphic as an F variety to a product of GL1. Okay, the group of invertible matrices of size 1. That is, well, if you put the F1 inside, then this is just F cross, the multiplicative subgroup. Sorry, the product of that. Yeah.
There should be some semi-simple condition of T.
Semi-simple. I think is it implied by the this
Multi-rule of GA.
Sorry.
Multi-rule of GA, the additive.
No, it's product, right? Oh, okay.
Yes. Yes, but it's reductive, so is it enough?
Yes.
Still,
Not
yeah?
reductive.
Yeah, a reductive, commutative algebraic group is always semi-simple. Oh, sorry. It's always
The torus.
Upper triangular. In GL2, the upper triangular.
The torus you can need.
but that's not reductive, right? It has a unipotent radical.
The G is reductive. The T.
For torus, I don't think you need.
Okay. Active reductive.
Semi-simple elements.
No, semi-simple is not commutative for this. Reductive is okay, but I don't think you need the reductive for the torus.
But if I add this reductive condition, then it guarantees the torus is a product of GL1 with this split, isn't it? Okay, is this okay?
Yeah, if you add the reductive, it's okay.
Okay.
Yeah.
Okay.
When you mentioned T always splits over the algebraic group, so according to this is a definition, but T always splits over actually over a finite extension.
Yes. Yeah. But I don't want to talk about the Galois theory in this course. So in the following, I'll always assume T is split. And actually, for the reductive groups that I have erased, all these split reductive groups. That means it contains a split torus. So I'll give examples. So for example, in GLN, we can take T to be a diagonal subgroup. Okay, so AI is in F cross. So this is a split maximal torus. It's isomorphic to GL1 n pieces. Okay. If it is the odd special orthogonal group, then a split maximal torus looks like this. So we have again it's a diagonal subgroup. So the first n entry, let me denote them by A1 to AN. But the equation, the transpose inverse equation, forces the last n entries to be something like AN inverse down to A1 inverse. Sorry, for some reason I want to talk about the odd special orthogonal group first. Okay, so then in the middle there's an extra entry. The transpose inverse equation forces this to be 1. Okay, so we have n 3 entries here. All these are elements in F cross. So again, this is isomorphic to a product of GL1 n pieces for SP2n and special orthogonal group 2n. A maximal torus looks like diagonal subgroup. given to an in the first n entries, and the equation forces the last n entries to be an inverse down to a1 inverse. Okay. So let's take these as examples. Whenever I talk about a maximal torus, then you think about this maximal torus as one of these.
And no other reason, other conditions for this AI in S4 to uncover. No, is it orthogonal? So AI module of AI 1. There are no other conditions for this.
I think the only condition is well, this middle entry is 1, and the last n entries are depending on the
and the transpose of the product of A and the transpose of A equal 1. Since it is orthogonal.
You want something like this? AI.
No other reason, no other conditions?
No? No, this is the one.
Because HT is a subgroup of SO2 and S1.
Yes.
So any matrix in SO.
Well, okay. So the equation is perhaps a bit different from the usual one, right? So this is the usual orthogonality condition because I take a conjugate by a certain matrix. So you check, this is the one. Okay, so here I consider the rational characters of a torus. So an F rational character. Okay, a character means a one-dimensional representation. Okay, so it starts from T to because I'm talking about F rational characters, so the image is in F. Okay. So such a character takes the form. So say if you have, if I put it this way, so I just use this tuple, this n tuple, to represent an element like this. Okay, so a character takes a diagonal element to the product of powers of each entry. So this A1 to certain power, K1, times A2 to K2 up to AN to KN for certain, for some integers, KI. Okay, so any rational character takes this form. So you can see the set of rational characters of P form an abelian group, a free abelian group. Actually, well, I divide it this way. So this X star T is the notation for the set of rational characters. And as a free abelian group, this is just set to the n, where of course any element k1 to kn represents a character like this. Okay, can you see that? So a tuple k1 to kn with integer entries represents a character.
Why the character is called a rational?
It's because the base map is defined over F. That means you can represent it by equations with coefficients in F. Yeah. Otherwise, if say if you consider F to be real, then you may imagine you can include something like an exponential map, which we don't want to include that in this case. We just want something that is polynomial-like. Okay, so rational characters. And here for convenience, I'll take a basis for that. So we take a basis. For the group of characters. So say I use this symbol EI, I from 1 to n, where EI takes a diagonal element to AI. Okay, just extract its I component.
What if T is not split?
If T is not split, I won't talk about that in this course. So there are some non-split torus, okay, that because I don't want to go into Galois field.
We can talk about it after.
Yeah, in the discussion or
yes,
yeah.
After the discussion.
Yeah. Okay. So we let this group, this torus T, acting on the formal Lie algebra of G. Okay, so consider the conjugate action of the torus T on the what we call the formal Lie algebra of G. Okay, so here I won't talk about the definition, but you can just imagine this is just like the usual Lie algebra. Say if it is the general linear group, then the Lie algebra is just the algebra of all possible square matrices. And for special orthogonal group, the Lie algebra is the matrices satisfying minus transpose equals to itself in the anti-symmetric matrices, and so on. Okay. So if you consider the action of T on the Lie algebra, then because T is commutative, so there are a couple eigenspaces that you can extract. So the eigenspaces give a finite subset in the subgroup. Okay, so what is this? This okay, I write it here. This set is the center of G. Okay, so the center of the group is just the element that commutes with all elements in the group. So this set in particular is contained in T, and this notation means all the characters of T which is trivial on the center. Okay, I'll give some examples. So if you don't understand the definition, you don't have to worry. Okay, so there's a finite subset of there's a finite subset in this subgroup. So so this subset is called the root system of T in G. Okay. So don't worry, I'll give examples. Perhaps I need these, so erase. So again, I'll use these classical groups. So in GLN, what is the root system? By the way, so I use this symbol. So this finite subset, I use this symbol capital sigma, T and G. So for GLN, if T is given by the diagonal subgroup, the root system is given by this. So EI minus EJ, where IJ they are between 1 to n, and I is not equal to j. So why is that? I give a short calculation, and then you can do it for other groups. Okay, so you let something like A1, A2, A3 acting on the Lie algebra.
What is zero TJ?
Say again?
What is zero TJ?
What if? Sorry, what if?
What is zero TJ there?
That? What is that?
Zero TJ.
No, I didn't. What I say? Oh, you mean all these EI, EJ?
You ask what is what is the root space system?
What is the root space?
No, not root space, but
what is generated? What is general case of zero TJ?
What is the general?
There.
These EI?
No, I mean the other.
What's that?
root system. He asked you the root system.
This root system, yes? It's sigma TG.
Yeah.
Yeah, this is the root system. Well, here. Oh, you mean G? sigma Tg.
The general form of root system.
General form of a root system. Ah, okay. The general definition.
Yes.
Maybe I won't give that in this course. Yeah. I try to confine things in examples. Okay. I don't want to give the full definition and it would be. I mean, it would be a bit difficult for some of you. Okay, so well, just take it as an example. This is the root system for the general linear group. Okay. So why do we have all these roots? Because, well, say if you conjugate a diagonal element to the Lie algebra, so this can be anything. I just take n to be 3, okay? So on the diagonal, the action is trivial. On the off diagonal, say in the 1, 2 entry, you see the action scaled by the A1 over A2. Okay, on the diagonal, then it's trivial. On the, say on 1, 2 entry, it's scaled by A1 over A2. That is E1 minus E2 on your diagonal matrix. Okay? You just read the powers. Okay, this is A1, A2 inverse. Okay. So this is one of these characters. And you check all the possible off diagonal entries, then you get all these EI minus EJ. Okay. So this is for the general linear group. For special orthogonal group, for the odd special orthogonal group, I'll just give you the answer, and you can check it as an exercise. So all these EI minus EJ, we also have plus or minus EI plus EJ. Okay. If you look at here, then you can see they are given by say taking AI here, and the inverse of AJ inverse here, that is just AJ. Okay, so you have A1 times AJ, and that is given by the, this character. And because we have this 1 here, we also have something like plus minus EI. Okay, well, of course, I cannot be J. Also for here. Okay. For the symplectic group, we also have EI minus EJ, EI plus EJ, but because we don't have 1 in the middle, you can check we have 2 EI. And for the special orthogonal group in even size, somehow these 2 EIs are gone. So EI minus EJ plus minus EI plus EJ. Sorry. I'll repeat it here. Okay.
Is there next, I mean, I minus EJ, yeah?
Mm-hmm.
The middle of it, can we put a minus on?
Minus EI, well, minus bracket of
Yeah,
EI minus
yes,
EJ is just the EJ minus EI.
Ah, yeah, of course.
Yeah. Okay. So one more terminology, then I'll talk about simple roots. So, notice that so for each eigenspace, this in symbol I call it G alpha. Sorry, it should be U alpha. Alpha, okay, where alpha is in the root system. Okay, this eigenspace, I mean the remember this eigenspace under the action of the torus on the Lie algebra. For each eigenspace, there's a isomorphism over F. Q, a certain subgroup in G, I'll denote it by capital U alpha onto a subgroup of G. And we call this U alpha the one parameter subgroup of G associated to alpha. Okay. So it's like an exponential map. For example, I just use the example here. So the 1, 2 eigenspace is here. Okay, it's a say in GLN, it's U E1 minus E2. Maps to here, where x1, 2, then all the other entries are 0. Just goes to, well, here in this case, it's just 1 plus this matrix. So it's 1 plus, I'll write it this way. Perhaps I'll give it a name, so E alpha. Okay, it's like an exponential map. If you give me 10 minutes, then I'll finish the topic for simple roots. So any questions so far?
What is in F as a morphic? Why is F?
F as a morphic?
Yeah.
I just require this map to be defined over F. So it's defined by
over F means it is a polynomial.
By polynomial, if you view it as varieties. Yes. Okay. So this is nothing but just mapping. Well, basically, it's just mapping this coordinate to itself, right? Okay. So simple roots. So there exists roots. Roots, I mean the characters in the root system. Okay, there exists roots, which well here. Okay, let me emphasize. There exists roots, which form a basis for this subgroup. Okay. Those characters trivial on the center, so we call these simple roots. In symbol, I use delta. Okay. So this is a subset in the root system. But there are many choices, but let me fix that. Let me fix one for each group. So for the general linear group, let me take this. The simple roots are ei minus ei plus 1, where I from 1 to n minus 1. Okay. So there are n minus 1 many simple roots. And you can see you can write any roots as a linear combination of these. For the odd special orthogonal group, you can take the same thing with an extra one here that is En. Okay, the one here. Okay, you can check any root here. It's a linear combination of these n simple roots. For example, you want En minus 1 plus En, then that is En minus 1 minus En plus 2En. Okay, I leave it for you to check. For SP, I take again ei minus ei plus 1 with 2En. For even special orthogonal group, same thing, but the extra one is En minus 1 plus En. this should be the last slide. So you can check any root is a linear combination with integral coefficients. Okay, it's an integral linear combination of those simple roots. Of the alpha here. So say if usually I use alpha I, okay, for simple roots. So say if alpha is given by this. Delta is the set of simple roots. Okay, for certain integers ki. Then we call the root alpha positive if all ki is non-negative. Okay, at least one of these is positive. If alpha is a positive root, okay, we cannot have all entries 0, okay, because we don't have 0 root in the root system. Okay. So at least if the entries are non-negative, then it's a positive root. And it's a negative root if all ki is non-positive. Okay, so you can check from the example. The root system is decomposed into two subsets. The roots are either positive or negative. We cannot have any root that is having mixed coefficients. Well, here each one has mixed coefficient, but if you try to write any of these as a linear combination of simple roots, then you'll find the coefficients are either non-positive or non-negative.
Positiveness and the negativeness of alpha is always depend on how we choose delta.
It depends on the choice of delta. Yes.
I want to know if there is some delta so that the last is not true.
No.
For any delta, this is true.
Simple
system always exists.
I know. I want to see if there is delta so that the proposition is not the case.
Well, I don't think so. If you follow strictly from the definition.
Yeah.
I didn't try, but I don't think you can do it.
So for any delta, sigma equals to sigma positive.
Yes.
Yeah, for any simple system, that proposition holds.
Yes. And in fact, you can see. Let me make a final note here. In fact, those positive roots appear in the ion spaces in the upper triangular part of your Lie algebra. Okay. So that means if alpha is a positive root, then this U alpha appears as an eigenspace in well, if you write a group in the matrix form, then it appears somewhere here. If alpha is positive. If it is negative, then it appears in the lower triangular part. Okay. So from the picture, you can see a root can be either positive or negative. Okay, so I'll stop here, and somehow I think I need one more class to talk about reductive groups. So I'll continue tomorrow. So yeah, if you have any question, then you can ask in this Q&A session. Is the speed okay? Is the speed? And the English, is it okay? Yes? Okay.